You know, at the turn of the 20th century, physicists pretty much thought they had it all figured out. The laws of motion, electromagnetism, it was like this grand, beautiful building that explained almost everything. But there were these weird little noises coming from the basement, a few unsolved mysteries that were about to bring the whole house crashing down and really shatter our entire understanding of reality itself.
So, to figure out what was going on, we've got to follow the evidence, just like detectives. Our investigation is going to take us through 5 huge breakthroughs that basically crack the case of quantum mechanics wide open. All right, so our detective story kicks off at a crime scene. And the victim? Well, it's the established laws of classical physics. The key piece of evidence? Something that physicists gave the very dramatic name, the ultraviolet catastrophe.
Seems like a pretty simple question, doesn't it? You heat up a piece of metal, it glows red, then it gets white hot. But here's the thing. When physicists tried to use their own rules to predict exactly what kind of light a hot object should be giving off, the answer they got was, well, it was complete nonsense.
See that dotted line? That's what the old physics predicted. It said that a hot object should release an infinite amount of energy, especially in the ultraviolet part of the spectrum. Now, obviously, that's not right. You don't get vaporized every time you stand near a campfire. This huge, glaring problem, this ultraviolet catastrophe, was the first big clue that the fundamental laws of physics were seriously broken. So enter our first detective on the scene, a German physicist named Max Planck. He was staring at this problem, and almost out of sheer desperation, he came up with a radical, and I mean radical, new clue to solve the case.
The craziest part is, Planck himself didn't really believe his own idea at first. He literally called it an act of desperation. He was just trying to fudge the numbers, to cook up a math formula that would match the actual data from experiments, that solid line on the graph we saw. But to do it, he had to break one of the most fundamental rules of physics.
Okay, so for hundreds of years, everyone just assumed that energy was continuous. Think of it like a smooth ramp. You could have any amount of it, big or small. Planck's wild idea was that energy is actually more like a set of stairs. You can be on this step or you can be on that step, but you can't be anywhere in between. Energy, he said, can only exist in these little discrete packets.
And he called that smallest possible packet of energy a quantum. His formula was incredibly simple. The energy of one of these packets equals a constant, which he called h, times the frequency of the light. Now, this little equation solved the ultraviolet catastrophe perfectly. But in doing so, man, it opened up a whole new can of worms.
Planck's idea was so weird that most physicists, Planck included, figured it had to be just some kind of mathematical trick. But then, a second equally baffling mystery popped up that was about to prove just how real his idea actually was.
This right here is the photoelectric effect. Scientists had known since the 1880s that if you shine light on a piece of metal, you can actually knock electrons right off its surface. The problem was, the way it was happening, it just made zero sense according to the old rules.
So if light is a wave, right, you'd think a brighter light, a more intense wave, would have more energy to knock those electrons out harder and faster. But it didn't. And you'd think even a really dim light would eventually build up enough energy to kick an electron out. But nope. If the light's frequency was too low, if it was the wrong color, nothing happened ever. Classical physics was completely stumped, again. And then, in 1905, this young patent clerk you might have heard of, Albert Einstein, he's the one who connects the dots. He takes Planck's super weird idea about quanta and applies it to light itself. He asks, what if light isn't a wave at all? What if it's a stream of these tiny little energy packets? Later on, we started calling them photons.
If you imagine light as a stream of tiny bullets, the photoelectric effect suddenly makes perfect sense. One photon bullet hits one electron. If the bullet doesn't have enough energy, nothing happens. But if it has enough, bam, it knocks the electron out instantly. Making the light brighter just means you're firing more bullets, not more powerful ones. With this, Einstein had just proved that Planck's quanta weren't some math trick. They were real.
So let's just pause here for a second. Light, something we all knew for a fact was a wave, could also act like a particle. This was the huge twist in our detective story, and it led to a question so bizarre, so profound it would change physics forever. If a wave can act like a particle, could a particle act like a wave?
I mean, that sounds impossible, right? Waves and particles are like total opposites. A wave is this spread out thing, like a ripple in a pond. A particle is a tiny dot, like a grain of sand. It has a specific location, a specific momentum. How could anything possibly be both of those things at the same time? Well, in 1924, this French physicist and honest-to-goodness prince, Louis de Broglie, made an absolutely breathtaking proposal. For his PhD thesis, no less, he suggested that maybe everything has both wave and particle characteristics. Not just light, but electrons, protons, you, me, all of it. And he captured this mind-bending idea in one simple, elegant equation. It just says that an object's wavelength, that's lambda, is equal to Planck's constant, h, divided by its momentum, p. Think about that. This is profound stuff. It directly connects a wave property, its wavelength, to a particle property, its momentum.
Now, a hypothesis that wild is one thing, but this is science. You need proof, cold, hard evidence. Could anyone actually detect this matter wave? This brings us to the final act of our investigation, the experiment that would finally confirm this bizarre new reality.
So, two American physicists, Clinton Davison and Lester Germer, they set up this experiment. They took a beam of electrons, which, remember, everyone knew were tiny little particles, and they fired them at a crystal of nickel, just to see how they'd bounce off.
The prediction was really straightforward. If electrons were just little particles, like tiny marbles, they should just scatter randomly in all directions. But if they were somehow waves, they should do what waves do when they hit an obstacle. They should diffract and create a very specific interference pattern of peaks and valleys.
And this, right here, was the smoking gun. First, Davis and Germer calculated what the wavelength of their electrons should be according to de Broglie's crazy hypothesis. Then, they looked at the pattern the electrons actually made and measured the wavelength from that, and the two numbers, they were a near-perfect match.
I mean, look at this. De Broglie's theory predicted a wavelength of 1.66 angstroms. The experiment came back with 1.65 angstroms. It wasn't just close, it was a dead ringer. The proof was undeniable. Electrons, things everyone knew were particles, were behaving exactly like waves.
So the verdict was in. That pattern you're seeing, with the light and dark bands, that's caused by interference, something that should only happen with waves. But it was created by a beam of electrons. The case was closed. Planck, Einstein, de Broglie, they were all right. Reality, at its very core, is so much stranger than anyone could have possibly imagined.
This discovery wasn't just a new chapter in the physics textbook. It was a completely different book. It just destroyed the old idea of a predictable clockwork universe. Instead, we got a universe governed by probability and just deep uncertainty. And it leaves us with this one final, profound question. If the fundamental building blocks of our world can't even decide if they're a wave or a particle, what in the world does that say about the nature of reality itself?